Welcome to the beginning of Chapter 11. We're going to start out with the basics of chemical equations. First of all, what is a chemical equation? Chemical equations are just quick ways of communicating information about a chemical reaction that could take place. They can tell you many things. They can tell you what chemicals undergo a reaction, and these are specifically called reactants. It can also tell you what new chemicals are formed during the reaction. They have the special name products. In addition to this, they can also tell you what conditions are necessary for a reaction to take place. Is it going to require excess heat be added, or perhaps the presence of a catalyst? We'll talk more about those later. Or is having a little bit of light going to be sufficient to start the process? They also can tell the states of matter of the reactants and product, and also can tell the direction in which the reaction will proceed. This table is a table of a lot of important symbols for you to understand in order to properly understand chemical equations. We're going to talk about several of these symbols now. Equations have two sides to them. There's the reactant side. These are generally shown on the left side of the equation. If there's more than one reactant, then we use a plus sign between them to indicate that these are separate chemicals. There are products. These are generally shown on the right side, and they're also separated by plus signs if there's more than one product being produced. The two sides are separated by an arrow. The arrow could be a simple one pointing to the right, just indicating the direction of the reaction. If the arrow has something written over it, then whatever's written above it is indicating the conditions under which the reaction proceeds. Is it going to require heat, light, or some sort of chemical catalyst like palladium or permanganate? Or you may even have a double-headed arrow, which indicates to you that the reaction actually can go either direction. Now, chemical equations can come in different forms, and many times we work through a sequence of equations to get to a final equation. Usually, we start with a word equation, which is just an equation involving words instead of formulas. It describes what's reacting and what's being produced. We can take a word equation and translate it into what's called a skeleton equation, which is where we take those words and we change it into chemical formulas. That way we have formulas shown for all reactants and products. Once we have an equation such as that, then we can take it and provide even more information about the reaction. We might provide information like the state of matter for the reactants and the products, or perhaps report necessary conditions for the reaction to take place. The presence of a catalyst being required, adding heat, adding light, any of those things. Now, a catalyst, all it is something that speeds up a reaction. It doesn't get used up in the process, but it does make the reaction take place at a faster rate than what it would naturally. If you were given the following reaction to describe, when methane gas burns, it combines with oxygen to form carbon dioxide and water. Then you could write a word equation. The first thing you would do is identify as you read it, what exactly is it saying is doing the reacting. And it says methane is burning and it's combining with oxygen. So that starts us with methane and oxygen as reactants. And it says it's going to form carbon dioxide and water. So those two things are our products. So our word equation would look like this. Methane plus oxygen yields carbon dioxide and water. That's how we would read that word equation. From that, we can create a skeleton equation where we insert formulas in place of each of these words. Now, we have to remember certain things, like the fact that some elements, such as oxygen, occur in a diatomic state. So when we write our skeleton equation, we need to make sure we're using proper formulas. In this case, methane is CH4, oxygen, as I just mentioned, is going to be O2, carbon dioxide is CO2, and of course water is H2O. Now, a chemical equation will give more information than that. Notice it said methane gas, so we know it's a gas. And we also know at most temperature and pressure combinations, oxygen and carbon dioxide are also gases. Now, notice next to each of those three that I just mentioned, there's a G in parentheses found after the chemical formula. And that's the way we indicate that those are reacting as gases and producing one of those things, carbon dioxide, as a gas. Water, however, is going to be produced, and if it's not at a high temperature, instead of it being a gas, it's going to come out as a liquid. Now let's try another problem. Hydrochloric acid and solid sodium hydrogen carbonate will react to form aqueous sodium chloride, water, and carbon dioxide gas. We can begin with a word equation. Before it says will react to form, before those words it has mentioned what the reactants are. Hydrochloric acid and sodium hydrogen carbonate. So those are our reactants. And of course our products come after the words will react to form, and we get sodium chloride, water, and carbon dioxide, so 3 products. And so our word equation would look something like this. We can translate each of these into formulas. Hydrochloric acid, remember it's named as an acid. Since it says hydro, we know that's a monatomic anion, so it's hydrogen combining with chlorine, and so its formula is HCl. Sodium hydrogen carbonate has the sodium ion reacting with hydrogen carbonate ion, which with a +1 on sodium and a -1 on hydrogen carbonate would go together in a 1-to-1 ratio, so it's just going to be NaHCO3. Sodium chloride, that's a +1 sodium ion and a -1 chlorine ion, so it has the formula of just NaCl because that will allow the charges to balance out. Water we know is H2O and carbon dioxide is CO2. So our skeleton equation would look like this. Note that each of the formulas I know have been written correctly because I considered things like, is it named as a molecular substance, an acid, or an ionic formula? And if we say an ionic compound, then we need to make sure that we're considering charges and we're making sure that we're writing the formulas correctly for those. The chemical equation would take this a step further and write in any of the states of matter. So when we say something's an acid, then it's dissolved in water. So that's a different state of matter. It's not liquid. It's called aqueous, or sometimes pronounced aqueous. Then it mentions that it's solid sodium hydrogen carbonate, and it forms aqueous sodium chloride. Water is never aqueous because aqueous means dissolved in water, and water dissolved in water is still just water, so that's liquid. And then carbon dioxide gas. So as you can see here, we have all 3 of our aqueous compounds mentioned. We have liquid for water, and we have gas after CO2. Here's a second problem to try. Hydrogen peroxide solution will break down in the presence of light into water and oxygen gas. So when it says it will break down, that means what came before it is what's reacting. In this case, it's just a single substance that breaks down into multiple substances. So we only have the one reactant, hydrogen peroxide here. We have 2 products, water and oxygen gas, as it indicates after it says will break down in the presence of light. So our word equation would look like this. Hydrogen peroxide yields water plus oxygen. Our skeleton equation would include our formulas, H2O2, which is hydrogen peroxide's formula. Water is H2O, and oxygen, remember, is a diatomic, so make sure you write it as O2. Having these formulas correct is essential, especially when we get to something we're going to be learning shortly, which is how to balance equations. Chemical equation for this would include any extra information, such as the presence of the catalyst, the light, and also any states of matter. Now, when it said hydrogen peroxide is in solution, a hydrogen peroxide solution, that means hydrogen peroxide is dissolved in water, so it's aqueous. And water, of course, would be liquid, and oxygen says it's a gas. So our chemical equation would look like this. We'll do this demo in class and work on this problem together as a class.